9.3, we're going to be taking a look at applications in probability. There are other applications. We're going to be taking a look at a couple of things in this section. And the first one that we're going to be taking a look at is odds. So we'll define what odds are, and then we're going to talk about where you've heard them used in culture, okay? So we're going to let P of A be the probability of an event. And then that would mean that P of A with the bar on top is the probability the event doesn't occur, okay? Then if we wanted to take the odds in favor of an event, then it's the fraction of the probability of A compared to the probability of A complement. Or if we apply a little bit of the formulas we saw back in section 9.1, this is the probability of A over 1 minus the probability of A. So these are odds in favor of an event happening. And then the odds against an event happening are just the reciprocal. Okay, the likelihood that it doesn't happen on top, the likelihood that it does happen on bottom. Okay, so where have you heard odds referenced in culture? There's lots of places. You're smiling like you want one. The odds of it raining. You hear people talk about odds of it, like weather conditions. That's one, sure. What else? I know you guys have heard these before. Okay, so gaming. So odds of a team winning something. So you see that used with sporting events specifically. One of the sporting events that you see it used with like considerably is actually horse racing. They use odds in horse racing a lot, but they use it in in gambling odds for like football games and things like that too. There's one more that everybody always wants to mention. So what is it that we're wanting to mention? Nobody wants to say it. Nobody wants to say it.
I was going to say Super Bowl.
Super Bowl. That one's one, yeah. There was a movie and a book series and Hunger Games. Everybody always wants to talk about the Hunger Games, so not a fan of that, but that's okay. They talk about odds in that sense as well. So it's really important to understand that odds is related to probability, but they're not the same thing, right? So when you're looking at odds compared to probability is the likelihood something happens compared to anything happening, right? Any possible outcome. But when we're looking at the odds of something, we're comparing the likelihood that it happens to the likelihood that it doesn't. Okay? So the comparison is a comparison to a different thing. So let's take a look at an example, and hopefully we can see how this works a little bit. So we're going to have a set of 8 marbles. 5 are red, 3 are white. Okay? So this looks a lot like the section 9.1 kind of questions where there were balls in a basket and whatever. So starting with the first question, looks just like section 9.1. What's the probability you'll choose red? So how many red marbles are there? 5. And how many total marbles are there? 8. So this is a 5 to 8 probability. Odds, however, compares the red marbles on top, it's still 5, to everything that's not a red marble. So what would the denominator be for this one? It'd be a 3. Okay, so the comparison is different. And in fact, it's a comparison we've seen before. Do you remember back in section, I was in chapter 6 somewhere, we talked about I think it was chapter 6, maybe it was chapter 7, now I can't remember. We talked about part to part and part to whole ratios. Does it sound familiar? It was in chapter 6, I'm pretty sure now. Yeah. So this is what we're looking at here. Probability is a part to whole ratio. You're comparing the part to the whole. And odds is a part to part ratio. Specific kind of part to part, right? Part to not part, kind of almost like that, but it's still a part to part ratio. So the comparisons are much the same as the things we've seen before, but they're presented with this phrasing as odds. Okay, so I think Catherine was the one who said something about rain. So that was actually one of my examples. Example number 2 talks about rain. So if you had the probability of it raining for the day as 60%, what are the odds against it raining? So this phrase against is important. It means that we're going to do something a little bit different. So when we're looking at the odds against, what we're saying is that we want to know the likelihood that it doesn't rain on top, like that's the likelihood, compared to the fact that it would or does rain on bottom. Odds against it raining. Okay? So what is the likelihood, the percentage, the probability that it will rain? What did it say? 60%. And you can even put it in as a percentage. It's totally fine. So what's the likelihood, percentage probability, that will not rain? 40%. And then we are going to reduce the ratio. Well, the percentages cancel out. That's friendly, right? And then we've got 40 over 60. Well, at the very least, right, the zeros cancel because you can divide them both by 10. What else can you divide by? 2. So 4 divided by 2 would be, and then we've got the thirds, right? Good. So we have 2/3 is our odds against it raining. Okay, all good? Theorem 9.8 talks about how odds and probability are related in another fashion. So if the odds in favor of an event happening are m to n, then the probability is m divided by m plus n. And if the odds against the event are happening are m to n, then we have the n on top and the m plus n on bottom. The difference in this description here, and the odds against part, we can ignore that for just a moment. Just look at the first one. The odds in favor is that we're going the other direction. Instead of starting with a probability and finding the odds, we're starting with the odds and we're going backwards to finding the probability. So let's go back to our very first example because it lends itself very nicely to seeing how this works. So right here we had, we had 8 marbles. We had 5 red and we had, and we had, what's that, yellow? White. 3 white. 3 white. So when we looked at odds down here, it was 5 to 3 because those are the only kind of marbles, right? Odds is 5 to 3. But if you actually take a look at what happened up here, you see that we had the 5 still on top. You have the 3 still on bottom, but look, there's the other 5 red marbles down there as well. Right? That's how we get 8. I mean, from that perspective anyway, that's how we get 8. And that's what you see happening over here on this description, is that we take the number of whatever we're comparing and we simply add them together on bottom. Okay, we're going to look at a 3-child family. We did 2-child family last time. We did 3-child family with my family too, so we've actually done this, but not with the specifics of this question. All right, so we want to have a look at finding the gender of children. Okay, so we're going to set this up as a 3-child family, so it'll look like the last one we had done last time in terms of the structure of the tree diagram. So the first set of branches is child number 1, and child number 1 would be a boy or a girl. And remember, the longer you make your branches, the easier it is to have enough space. It gives you more space, so I'm going to make mine long, like this. This is child number 2, and it's boy, girl. Boy, girl. And then we have child number 3. I'm still almost running out of space. Okay, everybody good so far? We can put the 1/2s along everything, okay? But we talked about last time when we were looking at a diagram where all of the branches are equal probabilities that we don't actually have to do it that way either. You can look at each of the outcomes because they're equally likely. How many outcomes are there here? Like how many ending tree branch locations do I have? 8, right? Did you count 8 over there? Yeah? So each of these branches is a 1/8 probability. Because they're all equally likely. Does that make sense? And if you think about it from multiplying, it works the same way, right? So this is 1/2 and 1/2 and 1/2. And what happens when we multiply 1/2 times 1/2 times 1/2? we get 1/8. Okay, so from either perspective, we're going to get 1/8 at the end of the branches. All right, so the question that we're being asked, though, is about odds. Let's take a look, because these 1/3, not 1/3, 1/2 and 1/8 are all probabilities. The question down here says, what are the odds of having all the same gender of children? So this is odds in favor, right? You want to have this happen, or at least in terms of finding the value. So these are the same, right? They're all the same, or there's some kind of a difference involved. So how many branches do you see that have all the same gender of children? 2. There's boys at the top, and there's all girls at the bottom. There are 2 branches that have 3 children, all the same gender. And how many branches have some mix of boys and girls? There are 6. So this is 2 compared to 6, reduces to 1/3. So the odds in favor of having all the same gender of children is 1 to 3. So then, what are the odds against having all the same gender of children? You just flip it. So you don't need to calculate anything again, right? These 2 things are reciprocals of one another. So if the odds in favor are 1 to 3, then the odds against are 3 to 1. Okay, does that make sense? We're all good? Okay, let's take a look at the second application in this section. Our second application in this section is called expected value. So if the possible outcomes of an experiment are A1, A2, up to AN, with probabilities P1, P2, up to Pn, then the expected value is the product of each of those values, right, times their probability. So A1 times P1, A2 times P2, and then we add them all together. So clearly, if we're going to do some sort of addition and multiplication here, we're talking about things that have numerical outcomes. So it doesn't make sense to talk about the expected value of this scenario. These are not numerical outcomes, right? These are people. This doesn't work. So when we're looking at expected value, we're looking at something that has numbers involved. So we see things like expected value, and we look at some kind of gaming situations usually, okay, or financial situations sometimes. And sometimes they're both, gaming and financial. So we see outcomes with numbers in them for these. And a game is considered fair if the expected value is 0. Okay, so it's not fair because it feels like it's, approximately equal. It's not fair because I like it. It's not fair because it's to my advantage, right? It's fair because I am just as likely to win as I am to lose. That's what makes it fair. Okay, and you can kind of think of fair as being sort of like it's completely random, right? It's completely random as to whether or not I would win or I would lose in this case. Equally likely. So we're going to do an example of a roulette wheel. This is our chapter on gambling, if you haven't told it so far, yeah, in different ways. So this is actually rather real life. When we get to it in just a second, I'll show you. On a roulette wheel, and if you haven't had a chance to be at a roulette wheel, that's even better. So I'm going to give you a little crash course. But on a roulette wheel, there are slots that are numbered 0, 0, and then 0, 1, 2, 3, 4, all the way up to 36. Okay? So how many slots are there? Let's just start there first. 37? More. There's 38. Oh, yeah. There's 38 slots. Does everybody see 38? 1 to 36 is 36, and then we've got a 0 and a double 0. Okay? So one way to bet, there's lots of ways to bet on a roulette wheel. You can bet on a specific number. You can bet on certain colors because they are color coordinated. You can bet on, and they're color coordinated by like evens and odds and things like that too. Okay, so you can bet lots of different ways. You can bet a series of numbers. You can say, well, I want to bet on 1, 2, 3, or 4. Like, so you can do that too. But one way to bet is to bet on a single number. That's our simplest way. That's one we're going to look at. If the ball lands, so you guys know what a roulette wheel looks like, right? You spin it, kind of looks like Wheel of Fortune, with the spinning thing, and then the ball lands in a specific location, okay? So if the ball lands on your number, then you receive 35 chips plus the chip you played, okay? So you bet 1, you get back 36, but one of them was the chip you already used to bet. So the net change in your pocket, what has changed in your world, is that you've additionally added 35 chips to your pocket. Okay? All right. What is the probability, first, that you will land on 0, 0? So what is the probability that we will land on 0, 0? 1 out of 38. Right? There's 38. What's the probability we will land on 0? Still 1 out of 38. Okay, it's the same thing. Okay, is everybody good with that so far? Okay, so you have a 1 out of 38 chance of landing on each individual number. So if I have bet on one of these specific numbers, I have a 1/38th chance of winning. Okay? Okay, so I'm going to show you how expected value works. All right, so this is not a lie. So my in-laws, they're not like addicted to gambling. I don't want you to think they're bad people. They're really good people. But they kind of view, they're, like on a cruise ship and you go through the gambling area or something like that. So it's not like they go to a casino or anything like that. But when my father-in-law sees a roulette wheel, it like beckons to him. Okay, it just does. And what he does is, so there's this like a marker board, if you will, or a scoreboard by a roulette wheel, if you've ever seen it before. And it shows you what it has landed on recently. So you can kind of see, hey, it landed on a 3, and then it landed on a 22, and then it landed on a 0, and then it shows the recent history. I don't know how far back it goes. When my father-in-law sees this board, if it does not show a 0 or a 00, so if there's no 0 or 00 on the score, on the history board or whatever, he thinks he should bet the 0 or the 00. This is what he thinks. This is a mathematical nightmare right here for somebody who has some knowledge about math. Because these are independent events, right? Absolutely no effect of one roll on the next roll on the next roll. But this is what happens. So what we're going to do is we're going to find out the expected value of his bet. So the chip in this case is worth $10, okay? So imagine if you had the $10, you're either going to lose $10 or you're going to get that $10 chip back, and you're going to get back 35 more. And 35 more chips at $10 a chip is how much money? $350. It's quick money, right? Or it's quickly losing $10, which would have paid for a meal at McDonald's. Just about right these days. Pretty close. Yeah. Okay, so we're going to take a look at what the expected value of a single bet on a roulette wheel is with these constructs, right? These conditions. Okay, so there's two options of what can happen. So this is expected value. It's not always a two-option thing. Sometimes, in some expected value situations, you could win a different amount of money in different situations. So I think you've got an example in your homework or group work where you're rolling dice, and if it lands on certain numbers of die rolls, you get like $5, and in certain other rolls, you get like $8, okay? So that's a little bit more long. I mean, it'll be longer consideration. It'll be more like this over here, where there's multiple things that you're considering, okay? But in our situation, for this one, with our roulette wheel, when we bet, we either lose the money or we win money. There's really only two outcomes. Are you with me? Okay, so we have the probability, we have the value of winning, right? How much money we win, times the probability of winning. That's one outcome. Right, is that there's that happening. The other possibility is that we have the value of losing. And it's times the probability of losing. Now, we've actually looked at this already a little bit in conversation. So let's piece in together the things that we maybe have already discussed. What is the value to me if I win the spin? It is $350. What is the value to me if I lose? Yeah, and it's negative 10, right? Because I'm losing it. So make sure you get a negative in there on that 10. Now, I don't want you to get tripped up with what I said before about the fact that you put the chip in, you take the chip back, right? If I put the chip in and I win, I get the chip back, that's not a gain or a loss to me. It does not count. But if I put the chip in and I lose money, right? And if I put the chip in and I win, I get the chip back and I get back 35 more. That's the 350. Everybody clear? Okay, cool. What is the probability that I will win if I bet on the 0 and the double 0? Good. It's 2 out of 38. Does that make sense? So then what is the probability that I will lose? 36 out of 38. Okay, so everybody understand? Okay, cool. So let's actually grab a calculator because it's going to do all the work for us. We're not calculating any of this by hand, okay? So you can put this in straight from the beginning to the end if you wish. If you want to take it in a couple of steps and do just the first multiplication and then do the second multiplication and then add or subtract in this case, that's fine too, either way. But we want to have, this is an amount of money, remember, right? So with money, how many decimal points do we use? 2. So we need to make sure that what we're recording is a 2 decimal point value, right? Okay. So what do we get if we multiply this out and add it together or subtract it in this case? It's dollar amounts.
The first one's 1842.
Oh, okay, we'll do it that way. 1842. And the next one's negative. Negative what? I don't have the numbers written down, the intermediate numbers written down, so. You sure the first one's, is $18.42?
Yeah.
Okay, I was like, I feel like I'm missing something. That makes more sense to me. So what is it if I do 10 times 36 divided by 38?
For the whole thing, I got $8.95.
That doesn't quite sound like what I have. It is. I guess I have something written down on my paper wrong. Okay. What was the last value, though, since we've already written it down? I'll put it in. 10 times 36 divided by 38. It's 947. Is that right? Okay, give me just a second. What's happening? I did do something wrong when I set it up. Do you see what I did? I got really excited and I just didn't read it out loud. That's what happened. It says he bets 1 chip on each number. That's what I messed up on. So in order to bet on the two locations, he has to put a chip on each one of them. Are you with me? Okay, that's my problem. Okay, so let's just fix that. So if he bets on each number, let me fix the problems, and I'll just fix them in red, just like I was doing purple grading on your papers, okay? The 350 isn't 350, because if he's putting a chip on each number, he's definitely going to lose one of those chips, right? So it's actually 340, because he loses one of the chips, he gets one of his chips back, and he gets the 35 more. And then if he loses, like, both chips, then he loses $20. There we go. So sorry. That's what happens when you don't read carefully. Okay, let's try again. All right, 340 times 2 divided by 38. I have 1789. And then the other one, is 1895. Here we go. That matches my number on my paper. It's amazing. Not only that, but it's the negative I was expecting as well. Negative $1.06. Okay, so what does it mean? Well, what it means is that for every time you play, if you played a whole bunch of times, like we talked in section 9.1 about Bernoulli's equation. Do you guys remember that? Bernoulli's law, sorry, they didn't call it that. Bernoulli's law of large numbers is what they called it. Does it sound at all familiar? This is the video I posted, so I hope it sounds familiar. It says that if you do something a large number of times, that the general outcome, like if you roll the die, like 100,000 times, that approximately 1/6 of the time it lands on the number 6, right? Or 1/6 of the time it lands on the number 2. So if I played this game in this way a large number of times, on average, I'm going to lose about $1.06 every time I play. That is the expected value. Now, that's not the outcome of any scenario, right? It's a large number kind of outcome. It is on the long haul. If I did this enough times, I would lose $1 approximately every single time I pulled this off. Okay? So are you going to win some? Probably. Are you going to lose some? A lot. But on average, you're going to lose $1. All right, we good? All right, there is another way you could set this up. You could set this up as the probability of, what happens when the die lands on the 0. What happens when the die lands on the double 0, and what happens when the die lands on anything else. You could set it up as 3 different pieces. I chose to set it up as winning and losing because it was a simpler version of what we could do, and we'll get the same outcome. So keep that in mind when you're looking at these, is that sometimes there's more than one way to set them up that will work as well. Okay, so this is a really good place for us to pause that gives you some time for your group work.